Hello everyone, welcome back to our Cube videos about internals of Cube framework, about internals of Cube library, about data files, the layout, data model, and. And in this video I will proceed explanation of data layout of .cubex file. In previous one I have explained that it is container, I explained a little bit about Anchor XML, and in the really previous video, which I will link here, I explained how the data layout in so-called data container looks like in the files .data, so metric data containers. And in this video I explain you how the compression goes over it. The compression has to be, of course, enabled or disabled, so I will show it also how the one enables compression or disables, and I will explain in the second part how the byte-wise layout of data looks like, so you perhaps can understand it, debug, and maybe write your own cube file reader if you need to. Okay, before we go on, I remind you, subscribe, press a like, and if you have any question, write in comments down there. Okay, so let's do the first part. So the cube consists out of multiple components: cube Java reader, GUI, which are first size, and we have a cube C writer library and cube lib library. C writer is writer, so it creates cube files only, and cube lib is general purpose library. It has to be able to read cube files and also create new one via tools or via GUI or anyhow. So, and therefore we have different levels of support of compression. In cube W writer library we can only enable cube compression or disable it, so there are only on off. And in cube lib library we either disable it, so then the library will not be able to read any compressed cube files. Enable it completely, it means it reads the compressed cube files, or not compressed, but produces also compressed cube files. And so-called read-only level of support, which means it is capable to read compressed cube files, but if it writes, if it produces new cube file, it is then in non-compressed form. So how do we enable or disable it? So for that we take a look in terminal. So first we go to C writer library. So let's take a look at configure command line option, and there is a command line option with compression or without, and that is the in, on, and off setting. Either it is on or either it is off. And in cube lib library it's the same, configure command line options. If we take a look here, we have full, RO, read only, none. That's, as I told you, the none, there is no support for compression, neither reading nor writing. There is a read only if we are able to read cube files which are compressed, but we produce non-compressed cube files. And full support means we are reading compressed cube files, also non-compressed, but we produce compressed. So we are doing that during configure time, because we either enable the compression code inside of the library or disable. So in the case there is no compression support, there is also no linkage to zlib library. For example, if the system doesn't have it. Very rare, but nevertheless. Okay, that is how you get the compression into your installation. So after that, cube is capable to read or write compressed cube files or not. And how does it look like on actually layout? So basically second part of this video. Again, comment, write, subscribe and like. And how does it look? Okay, so now I explain you compression is actually organized in our .cubex file. So if you remember from previous videos, our .cubex file is actually tar container which consists out of multiple files, and cube defines the specific files which are stored. So let's take a look. Zlib compression, wrong. Zlib compression in cube file. So if you remember, we have different files. So one file is, let's see, like that, XML. So this is a Anchor XML, describes dimensions of cube file, definition of metrics, definition of call path, regions, and everything. Another files, pair of files we have here. Okay. Another file is hashtag. I will call it hashtag. Actually, it is metric ID. So index, and we have hashtag very same metric ID data. And there are multiple of them, so they are going pairwise for every metric, metric 0, metric 1, metric 2, and so on and so on. We have index file which describes how which actually data rows are stored and where they are located. And we have the actual data rows which are stored inside of the data file. And then we have here so-called, I call them MISC files, multiple of them. That is any another additional file which might be useful for measurement, miscellaneous. So in this all these three files, so Anchor XML and miscellaneous files, we always access them as a whole, from 0 position to the last one. We take this data and provide and process as one. So Anchor XML goes to the parser, and the miscellaneous goes to the user, basically. So from 0 to the last byte, we do not seek there, we do not read partially, once to one. And therefore, these files, I mark it like this, they are compressed completely as a one big buffer via zlib algorithm, or in this case it is gzip algorithm, meaning if you remember that .cubex is a tar file, you can unpack it, you will have these files are separately, and then you can use the tool unzip, and then you obtain the non-compressed version of these files. It's just for debugging, for example. But they are compressed as a whole, because we always access to this data as a whole, no partial access. Index file, not where it is, we do not compress at all and never, because even in extreme case of having millions of data rows, the compression of this data doesn't bring much to the compression performance. We do not gain anything by compressing this data. This data is simply too little, too small. So therefore we simply ignore it and do not compress. And the last one, this data here, I write a special format. We apply compression, but we do not apply compression as in a case of Anchor XML or miscellaneous. We apply it in special form. So if you remember, just said the data is organized row-wise, and we cannot simply compress it everything at once, because we need to have random memory access. So therefore, I am not going to explain you how this gzip compression looks like. It is simple. The whole buffer is compressed, as I just told you. I will explain you in details how this special format looks like. Before I go on, compress, subscribe and like, and now we go. Okay, so let's take a look to the .data file, how it looks like. Okay. A reminder, some small recapitulation. our data is stored row-wise, which means we have for every call path for which we actually store data, we store so many data values, how many locations we have in system tree. So if in system tree we have 100,000 locations, then it will be 100,000 values, and each value has n bytes. This n bytes depends on the data type of the metric. So if the metric has a doubles as a data type, time for example, then it would be 100,000 doubles. If the metric is integer, like for example number of bytes, number of visits, then it will be 100,000 of integer. If the metric is ratio, complex, or anything else, then it is an correspondingly complex data type, but it will be 100,000 of them. And that makes the whole row of data is of a fixed size, and that's always the same for every call path what we are storing. So therefore dot data, as just a reminder for you, looks like that. Opla, I wanted to glue here. First comes magic word, and in the case of non-compressed form, that is cubex.data, and it is these are 10 bytes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And after that, our rows of data are stored. So row 1, let's do it in, let's say black. Where is my black? Come on, here is black. Yes, this one. So one row, another row. Well, actually it is like here. Then this row, then this row, and so on and so on. And that is the row 0, row 1, row n minus 1, row n. So these are rows of data which are being stored, and these rows are given by index file. The index file describes which rows are actually stored. So if it is dense, then all of them. If it is sparse, then it lists the C nodes which are actually having data and the sequence where they are stored. So, and then every row then has one value, second value, third, and minus 1, and so on and so on. And that is the value for location 0, location 1, location 2, and so on, location n minus 1, location n, and so on and so on. And each of this value is defined by the data type of the metric. As I just mentioned, it might be double, so 8 bytes, it might be long integer, 8 bytes, it might be short integer, 4, 2, 1 byte even. It might be the complex value, and so on and so on. Important is that it is the same within the metric, and that is within the data file because it's specific for the metric, and always for all locations. So therefore it has always the same number of these values. Every value has the same number of bytes, and therefore every row has the same size, and therefore we know which data is located. We can always access to it by having the ID of the call path and location. So if our library would like to have a data of call path, let's say 10, and location 50, then already these two numbers, they allow us to read from the file exactly the data value for this combination. Of course, it is not directly, we have to do a lot of transformation, but we're using by using this .index file, we can find out in which row is the data located, then we can seek on the 5th position and then read it. So that's basically idea. So that's the reminder how the data layout looks like in a .data file, and now how compression goes over it. as I just told you, compression is the intermediate layer which can be enabled or disabled, and it kicks in exactly on this between the reading from the file to the providing this data to internals of Cube library. So in this case, I speak about Cube general purpose Cube library. By Cube writing, it's coming from the library on the file. So here are two things which we have to keep in mind, or two requirements. So one requirement, the library has to have random data access, random memory access if you want so. Why? Because different tools, they do different processing of this data. Some of them they are doing call path-wise, some of them are doing row-wise, some of them have completely weird aggregation of data. The GUI has massive parallel access to the data. If we enable clustering, for example, which is the topic for the future, then the data for one call path is actually distributed across the system tree and opposite. So there is a absolutely wild mixture of data, and so therefore the data has to have or the library has to have random access to the data. So let's say we need the random memory access. So that's important thing. And another thing, if we take a look at this data is organized row-wise. So in one row there is a data for one specific call path in most cases. In the case of clustering, it's not the case anymore, but in the case of non-clustered cube, the data belongs to the same call path. So what does it mean? That is usually one region or one call which is being executed by rank 0, rank 1, rank 2, rank 3, and so on and so on. And then the row 2 has another call path, which is MPI send, for example, and it's executed by different ranks and so on. So, but what does it mean? It is to be expected that data within within a row has the same, let's say, properties. Most likely, they have the similar values. They are varying around similar similar value and similar range and so on and so on. So what do I mean? So for the row, let's say 0, we have the data values distribution probably in this range. And then for the row 1, which is like here, we probably have the distribution of values somewhere here. For the row like 2, maybe somewhere here. For the row 3, maybe like this or something like that. So what do I want to? What do I mean? The biggest contribution to compression performance, so basically to this ratio of compression, comes from the actually similar data. So it is coming from the data within the row, and not so like from here, or from here and here, and not from this actually gap between the rows or this. Yeah. So we made the experiment. We just took the data which is distributed row-wise, and we compressed it as one, or we compress this clusters of similar data. So in our case, this rows, and the compression was not really differing. So the 99% of compression performance is coming from the similar data or from the data within the row. And therefore, these are our experiments and our requirements, which means that we do also row comparison So we do also row-wise compression. It allows us to still access data in a random manner. So we can access to row 0, then row 5, from row 2, and end. And we do not lose anything in compression, or we do not lose much, because the biggest contribution is coming from the similar data, from biggest contribution to the compression comes from the similar data, so from the data within the row. Okay, so what does it mean now? Now I actually show you how the layout of .data in the compressed case looks like. Before I do it, again, comment, press like, and subscribe. Okay, let's do it here. Compressed data compress like that. Okay, as in previous case, in the beginning goes magic word, because we have to distinguish whether data is hours data from cube files, and we have to distinguish whether it is coming as a compressed form or not. So we have also magic word. In this case, this is a little bit different, is set cubex data. 11 bytes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So one reads 11 bytes, and if it is set cubex, then it is compressed form. If it is cubex data, which is 10 bytes, then it is not compressed form. So if it is not compressed, we know that after that we have row by row by row data, how they are described in the index file, and the data type of the metric tells us exactly byte-wise the representation. So what's about the set cubex? Of course, it is also row-wise, but now every row cannot have the same size guaranteed, because, for example, the row which consists out of 1, 1, 1, 1, 1, 1, or 2, 2, 2, 2, 2, or something, can be compressed way more efficient to way smaller buffer than, for example, row which consists out of scattered double data. I don't know what's a time metric, for example. It will be compressed in different size. And also within the doubles, for example, the double which varies only in last bytes will be compressed more efficient than the double which where every byte is varying. So therefore, also within the metric, one single metric, every row might have different size. So therefore, we cannot expect that our rows have the same size. They have different size. Okay, then how can we access them row-wise? Right, we have to have some kind of another index which describes or which creates connection between non-compressed representation to the compressed representation. Reminder, the compression is a layer, intermediate layer. Internally, cube library works with non-compressed representation of the data, where it takes IDs and it can it asks for basically the data. Then the library kind of calculates where this non-compressed data would be, and if it is non-compressed, it just reads it from there. But if it is compressed data, this intermediate compression layer kicks in and makes transformation from non-compressed representation and compressed, and then we read the data from the compressed cube file, this data file, and then uncompress it, and then provide the data back to the library. So how does it look like? It means then after that we have so-called compression index. So that's basically a piece of data which describes our compression, and because we do it row-wise, it's an index for every row which maps basically its non-compressed representation to its compressed representation, so that it allows us to find this row. And after that we have actually row by row, like previously, just that is row 0, row 1, row 2, row n minus 1, row n, and so on. Now this time I cannot say anything about bytes layout because R0 is different, has different size at R1, for example, because it is compressed larger. And what's about the bytes there? I cannot say anything. They are compressed. So therefore, I cannot say where the data for the value 5 of location 5 is. I know it's only that this is compressed buffer for the row 0. So I have to uncompress it, and then I get the non-compressed representation of this row, and then I can seek to the 5th position and then get the data for the 5th location. So that's the basically idea. Okay, so what's about this compression index? This compression index, that has basically, that is a sequence and so on of triplets. So it has the same number of entries. How many rows do we store in this data file? How many rows are described by the index file? So it's either all of them, so how many call passes we have, or how many have non-zero value, then it is given by an index file. So many entries do we have. So that is the entry for row 0, that's the entry for row 1, that's the entry for row 2, that is the entry for row minus n minus 1, rn plus 1, and so on. And every this triplet, 64 bits, so 8 bytes. 8 bytes. So it has 8 bytes long big integer, so 3 of them, and every of this triplet, let me write here somehow. Every triplet like this has 64 bits. Position of this row to which it belongs to, so in this case it's either row 0, row 1, in non-compressed case, so non-position, non-compressed. Then position in compressed case, another 64 bytes. And size of compressed row. So in non-compressed case we know the size from the very beginning, but in compressed also 64 bits, so 8 bytes, and that is size compressed. Yeah, so we have then n such triplets. Every of these triplets has 64 bits, and this describes position in non-compressed case, position in compressed case, and the size of compressed case. As I mentioned, that is the intermediate layer, so the library calculates the position of compressed or non-compressed case where the data is located, and then it makes either, if it is not compressed, it goes to reading directly, or if it is compressed case, it first transforms. It basically finds out where it is located in a case of compressed case, and it tells also the size of compressed row. So if we previously need, for example, the data for the C node 1 and location 10. So we would have to find a row which belongs to C node 1. And then we would read this row, and then we get the 10th position of the data for the location 10. So now we are going to where position of the C node 1 would be in the case of non-compression. Then we find it in using this index position where it is in the case of compressed. We basically go to this place, and then we know the size of result of compressed buffer. We read it, we uncompress it, And now we we go to the 10th position and deliver the data for the 10th location. Okay, so that's basically the whole magic. Yeah, we have magic word. It's different. We have then compression index, which consists out of triplets. Every triplet has 64 bits, and after that a sequence of rows. But this time the size of the row is different, is individual, and because it is the result of individual compression of this row. And this compression is described under this index, and that allows us to have random memory access for the data. And because compression is coming from individual rows, then we gain, of course, our compression in the size. Here, maybe the last words. The magic or power of default setting. We, by default, do not enable compression because we have basically made measurements. The gain in the reading time for less data after compression is compensated by the time of needing to uncompress it, and therefore in runtime we actually do not gain anything. But if the size on the file on the disk is actually a point for you and you have to optimize it, then it is better you enable it, and then you produce simply smaller cube files. And then this layer will be then active and you will have compressed cube files. I hope you understand the details of compression in Cube. If you have any question, please comment, press a like and subscribe, and see ya next time.